Okay, our next talk is on formalizing graph algorithm with coinduction given by Oisín Kidney. Mike? Hello?
Oh, okay. Sorry. All right, thanks very much. Hello, my name is Oisín. That's me on the left. And this is the presentation for formalizing graph algorithms with coinduction. This is joint work with my supervisor, Nick, there on the right. And thanks everyone for coming. So this is a paper about graphs. Specifically, it's about functional programming and formalizing with graphs. Split into two halves. The first half of the paper is basically about a functional treatment of graphs. We use a pretty standard representation, but we think we have some new ideas about algebraic and design and coinduction. Second half of the paper is about our formalisation in cubical Agda. That's where most of the technical stuff is. I'm not really going to go through that in this talk. This is mainly going to be about the first half. All right. To get started, I want to talk about representing data structures. And I want to make an observation, and that's that functional programmers, like me, really like trees and lists, right? We go crazy for them, right? So things like this, and I mean, we have good reason, right? Like a simple data structure like this has a really simple, declarative, and clear data type on the right, and there's no compromise with the data type representation. The abstraction isn't leaky, okay? And also, it's inductive, and we really like inductive stuff because our languages are well suited to it, they support pattern matching well, and this guarantees termination as well because we're using structural induction. So we really like trees and lists. Graphs, on the other hand, don't do so well. So if we look at this kind of graph, the first problem that we'll have is that we have no nice kind of inductive type representation. So we can try with something like this, where basically representing a graph as a tree, where every vertex is paired with its neighbors, so the outward edges. So if you see here, we have the graph, we pick the vertex A, and then we have the two outward edges to B and C. And this looks okay, but our choice of A here is arbitrary. So we could have just as easily picked C as a central vertex. And this is a problem for formalization. So we don't have a canonical representation of graphs. We also have to deal with cycles, which is a problem. So I should emphasize that this can work well for functional programming. Representations like this kind of form the basis of the most comprehensive graph libraries in Haskell. But for formalization especially, the lack of a canonical representation and the presence of cycles are a real significant problem. So our idea was this. What if we just give up on induction and look at the cooler, more mysterious coinduction? And that gives us this kind of a representation. So a graph with vertices of type V is a function from a vertex to its neighbors. So neighbors here is just a type representing weighted sets. So this isn't a new representation, this is pretty standard, but the neighbors type is new, and some of the infrastructure we build up around this is new. So let's look at an example. So we have a graph here that has three vertices and 4 edges. And we represent that with this function. So every line in the function tells us the outward edges from a single vertex. So if we look at A, So yeah, if we look at B, we have a single edge of weight 4 to C. Then if we look at C, we have a single edge of weight 1 up to B. So this is an extensional representation. So it's a slightly different style to the other one. We're not listing the constituent parts. We are saying, if you ask me about a vertex, I'll tell you about it. It's a different perspective on things. Another thing that I want to point out is the type of vertices themselves is the same as the vertices of the graph, right? So this graph has 3 vertices because the cardinality of the vert type is 3. And the other thing is that this is coinductive. So it can actually happily deal with infinitely sized graphs, like this one. So we have IG for infinite graph. And this is a graph where every integer n maps to n plus 1 and n minus 1. Cool. So I want to give just a little bit of detail on the neighbors type. So it represents possibly infinite weighted sets. The weight here is drawn from a monus, which is a monoid that has this kind of partial subtraction operator that you see up there with the dot minus. So 5 dot minus 3 is 2, but then 3 dot minus 5, it truncates and you get 0. And it's also ordered using this thing called the algebraic preorder. The set itself has two kind of quotient laws. So it ignores order. So 7b, 2c is the same as 2c, 7b. And when you have duplicate keys, you keep the one that has the lesser weight. So that's the second example there, 7b, 2b, we keep 2b. Okay? So to define this type in Agda, we use higher inductive types and quotient types. But if you wanted to do this in Haskell, you could do just the standard trick of defining a new type synonym and promising that you'll be very good and obey all of the quotients and not do anything wrong. And so all of the algebraic stuff that we're going to do on the next few slides totally applies just with this type. In the future, hopefully something like quotient Haskell will be able to make this solution a little bit better. Right, now that we're up to the speed with the basics of the representation, let's talk a little bit about how the algebraic design comes into it. So a big inspiration for this paper was this paper, Algebraic Graphs with Class. And the idea here is to build graphs out of algebraic primitives, in particular the connection monoid and the overlay monoid, or arrow1+. So you can see two graphs as an example there. And you see that graph, 1 pointing to 2 and 1 pointing to 3, is built from these kind of atomic parts, 1, 2, and 3, just with the simple operators of arrows and plus. So we really like this algebraic approach. You get all of the advantages of algebraic abstraction, laws, initial objects, and so on. But it didn't seem obvious at first as how we would apply it to our thing. In the Mokov paper, they start with the algebraic stuff and they derive a few representations. We've started from the representation. So the solution comes in the form of arrows. So arrows are a thing, abstraction kind of similar to monads or applicatives, but they're better known for abstracting over pipeline-like things, so parsers or circuits. And the interesting thing here is that the graph type that we've already defined itself actually is an arrow. It's a Kleisli arrow relying on the monad instance for the neighbors thing. But the main point here is that all of the algebraic operators that we're looking for, all the things that we need, can all be actually found in control.arrow Haskell's arrow library. So let's look at one of those operators now. This is the overlay monoid. It's called that because we basically overlay two graphs with the same vertices on top of each other. So here's its signature. Notice that it takes two graphs with the same vertices. And here's an example of it working. So we have two graphs. Each of them have 3 vertices. And we're basically placing one on top of the other to get the thing on the right there. So notice that the edge C to B is preserved from the input to the output. And then notice that the edge A to B, when the two edges collide, we take the smaller of the two weights. So this monoid exists pretty much as is in algebraic graphs with class. But also, it's taken directly from the arrow plus class. So we didn't need to implement anything other than some new type wrappers in order to get this algebraic thing totally for free. And if you want to make it into a monoid, the identity that you adjoin is a graph with no edges. The other monoid that we have is the connection monoid. It's a little more complicated than the overlay monoid. Again, it takes two graphs. But what this one does is it connects the ends of edges of the left graph to the starts of edges of the right one. So if we see an example here. So we see we have two graphs here, each with 4 vertices. And we have one edge in the output. So that edge in the output comes from this edge in the input A to C, and then this other one, C to D. And then using the magic of animation, we can see that it makes this edge in the output. And the weight of that edge is the sum of the weights of the other constituent edges. So this weight is also in the input, but you'll see that there's no corresponding outward edge from B in the other graph, so we've no edge in the output corresponding to that one. So this operator is actually even more fundamental than the overlay one. This is a Kleisli composition. And again, it's taken straight from the R library. The identity in this case is a graph where every vertex points to itself. Cool. So the two monoids that we've seen, overlay and connection, combine to form a semiring. So semirings have been used with graphs for a long time. This is just two example papers that we have here. But also, actually, there are a load of other semirings on the graph type that we've defined that we can just derive again from the R library, right? So like we have this one. Notice that in this one, the type of the vertices changes on the output. So we actually multiply the cardinality of the vertices to get the output on the right. So pretty much all of the operators in the library can be interpreted, in the R library rather, can be interpreted as graph combinators or graph transformations. Okay, now we know how to construct graphs. Let's look at searching through them. So the first thing to notice is that because of our type of graphs, there's a symmetry that we can exploit to get a nice kind of uniform interface, right? So if we look at the type here of depth first search, this is an algorithm that takes a graph, takes a vertex to start the search from, and then returns a list of the vertices in depth first order. So the first thing we're going to do is we're going to generalize this a little bit. And now it's going to return the vertices also tagged with the weight, so the weight of the path it took to get them. Our type of graphs is actually V to neighbors V, or A to neighbors A. So this search thing itself is actually just a graph transformation. So this kind of uniform interface will give us a really nice way to compose combinators to develop search algorithms, which we'll see in a couple slides. Okay, so let's see an example of search on an actual graph. So it's the same graph that we've seen already. And if we call search on it, you'll see that the output is what you would get if you walked through the graph. So this one is in breadth first order, where you start at A, and then you go to C, and then B is the next one, and then B again, but around the other way. So if we look at this entry in the output, that comes from this path along the input. But of course, this search algorithm itself is producing a graph. So the natural question is, what does that graph look like? And it's this. So you see that this edge, this path that we have from A to C and C to B, that corresponds to an edge in the output graph here. Okay. So what we've actually done here is we've defined transitive closure on our graph type. And transitive closure itself can be defined in terms of the semi-ring operators that we had previously as the Kleene star. Okay, so all of this semi-ring language that we have on graphs itself can be used not just to define graphs, not just to build graphs, but also to define search over graphs. So the other advantage of our uniform interface is that it makes it easier to build search components that we can combine to make algorithms. So we have, for instance, this one. This is, again, just another graph transformation. And what it does is it attaches to each vertex the path that you took to reach that vertex. So if you had a search algorithm that searched through a graph and then returned individual vertices as a result, just by sticking this path combinator somewhere in that algorithm, now that algorithm return the paths in the result. We also have this one. This filters out edges from a graph according to a predicate. It does that by generating a new graph where there's a zero edge wherever the predicate fails. So we can combine these things to make pretty complex algorithms in this compositional and algebraic way. For instance, here's Dijkstra's algorithm. So it again is just a graph transformation. And what we have is we take in a graph, we say, okay, remember all the paths through this graph. Then also get rid of any paths that have a duplicate vertex in it. And then on top of that, find the transitive closure of that expression. And this gives you the shortest paths through your graph. Cool. So I'm now just going to very quickly run through the formalization that we have. I think this stuff doesn't translate so well to slides or a talk, so this is just going to be a brief overview. So the neighbors type makes up a bulk of the complicated stuff in the formalization because of the combination of quotients and coinduction. When we're doing coinduction, especially in Agda, a lot of the time we're relying on things like guarding under a data constructor or something like that. And when you mix quotients with that, it can destroy the kind of the uniformity of data representation that you might rely on in order to make coinduction go through the productivity checker. So what we actually do is our neighbors type is defined in terms of semi-group actions. So here it is. It's a dependent pair where the first part of the pair is a function, which is basically a search procedure where you give it a weight and it searches up to that depth that you've supplied. And then the second part is a neighborly, which is a coherence condition that says the first part has to actually be equivariant. Yeah. So also in the paper, we have stuff on using the monases that we had earlier to do well-founded recursion. And we also use the theory of completely iterative monads to give kind of justification for termination on recursive equations like the Kleene star that we already saw. And that's my time. Thanks very much.
Okay, we have time for one question. Who's there first?
Quick question. Where's the? Hi.
Go ahead. Answer the question.
Sorry.
Quick question. The definition of a graph is basically identical with the definition of a relation. It just is a relation. That's it. So, what does your work have to say about all the classical work on relational algebra and manipulations of relations?
Yeah, so I mean, it's obviously very related, and there's a lot of overlap between the two. The main kind of technical stuff that we were struggling in the work was with coinduction. So this idea of if you're relying on a coinductive definition from the get-go, how do you make all of your other proofs go through and so on? So the overlap with relational stuff, you get a lot of interesting things in terms of the algorithms you can define, but the coinductive stuff that we did in the paper didn't have as much overlap. That makes sense.
We have time for more questions because there's some technical problems. Please pass the microphone to.
Thanks for the talk. You talked a lot about how to define functions and define graphs, but not so much about reasoning about them. So how difficult is it to prove properties of the algorithms that you define in terms of those combinators, for example?
So it's complicated. The main stuff that we rely on is the semi-ring thing and the semi-ring laws. So we rely on the fact that in our formalization, search is basically identified with the Kleene star, and then we rely on the laws and the algebraic laws that you get as a result of that. And then the completely iterative monad stuff gives us the well-foundedness of each step and that kind of thing. So yeah, so pretty difficult, but yeah.
Thanks.
Do we have time for one more?
What was the motivation for using this the the edge weights that were drawn from a monus, like that structure didn't seem obvious to me a priori, like when you're dealing with graphs in general.
Yeah, so the reason that you need, we need an order on the thing so that we can talk about shortest path. And then we also need to be able to talk about the difference between two weights, because if we have two paths that are one slightly longer than the other, when you do something like put the other path back into the heap, usually you want to use the difference between the longer path and the shorter one when putting it into the heap, rather than the absolute weight of each one individually. So that's why we need the dot minus operation.
All right. Thank you. Let's thank the speaker again.